push that rock here with some math. Go Wildcats. So, last semester we studied the concept of a function and we studied its inverse. Let's look at this function here where we add 1 to the input, we take the cubed root of the input, and then we subtract 2 to find the output. So if I put in -1, then I have -1 plus 1, which is 0. The number that multiplied by itself 3 times gives you 0 is 0. And then subtract 2, you get -2. So when I put in -1, I get out -2. Let's do this one. Here, I'll show the work. So it's the cubed root of put in -7/8 for the input plus 1 minus 2. So we do what's in here first. This vinculum, which is this bar right here, is called the vinculum, is a grouping symbol. So it says do what's under the vinculum first. So I do this first. Well, you take away 7/8 from a whole and you get 1/8. Then we do the cubed root because it's an exponent before we do subtraction. So we take the cubed root of 1/8, which is find the number that multiplied by itself 3 times will be 1/8. Well, 1/2 times 1/2 times 1/2 is 1/8. So the cubed root of 1/8 is 1/2. And I don't know why I put a equal sign there. It's supposed to be a minus. -2. And then finally I subtract. 1/2 minus 2 is a -1.5 or -3/2. Okay, so we're doing the same thing. Put in 0, you get 1. And the cubed root of 1 is 1, minus 2 is a -1. Put in 7, 7 plus 1 is 8. The cubed root of 8 is 2, 2 minus 2 is 0. Put in 26, you can tell that I'm choosing very judicious choices for my inputs, you know. I put in 26 because I know it adds 1 to it, and I'll get 27, which is a perfect cube of 3. And 3 minus 2 is 1. You know, so maybe we should do one that's not so perfect, so I'll just pick any old number at random. Well, in that case, I get the cubed root of 51, which cannot really be written as a decimal. You know, it's not a perfect cube, minus 2. So that's what I get. What is this about? Well, 64 is a perfect cube of 4, so it's almost 3. You know, so this is almost 3. You back off to your... Wait, it's almost 4, back off to your almost 2. So it's bigger than 1, but smaller than 2. Okay. But anyway, let's move on. So here I have the function, and I'm going to find its inverse. So find f inverse. This does not mean reciprocate. Okay, it does if this was a number. Yes, 1/2 to the -1 is 2. But, or 2/3 to the -1 is 3/2. But this isn't a number. This is a function, and it no longer means that. Okay. So what does it mean? It means find the function that will interchange the x's and y's, okay? Or find the function that composed with this function gives me the identity element. And the identity element under composition is x. More about that later. So right now we're just going to walk through the steps for finding it. First, we admit that that's a fancy symbol for y. We use x's, I mean, not always, but traditionally and in this class, we've been using x for input, y for output. Since we want to swatch x and y, the inputs and outputs, we want this function to take all the inputs and make them outputs and all the outputs and make them the corresponding inputs. We will swatch the variables that we use to represent inputs and outputs. So I swatch the x and y's position. Now I'm going to solve for y. So I have to undo PEMDAS. So subtractions first, add 2. Exponentiation would be next here. So I'm going to raise both sides to the 3rd power. And if I raise this to the 3rd power, well, the cubed root and the 3rd power cancel out. And then I subtract 1. And so the inverse function, the inverse of f function, is x plus 2 cubed minus 1. Remember that from last semester? Hope so. So now here's our table that we got on the first page. And what we want to do is see if this output is paired with this input only, with this being the input now and this being the output. So we'll put -2 up here. Well, -2 plus 2 is 0. 0 to any power is 0. Well, 0 to any non-zero power is 0. So 0 to 3 is 0, minus 1 is a -1. Sure enough, it worked. The -1, -2, swatch to -2, -1. Put in -3/2. So we get negative 3 halves plus 2, and it's being cubed, minus 1. Well, negative 3 halves plus 2. 2 is 4 halves, so I get 1 half, and it's being cubed. 1 half cubed is 1/8. 1/8 minus 1 is a negative 7/8. Oh, great. Put in negative 1 plus 2, you get 1, because you take away, when this is negative and that's positive, you take away. So negative 1 and 2 make 1. 1 cubed is 1. 1 minus 1 is 0. Put in 0, I have 2. 2 cubed is 8. Minus 1 is 7. Put in 1. 1 plus 2 is 3. 3 to the 3 is 27. Minus 1 is 26. So everything worked. What was that other one we did? I think we did 50, and it came out to be the cubed root of 51 minus 2. Okay, well, let's put this in as an input. Okay, we're going to put that in as an input and see what we get out. So I put in the cubed root of 51 minus 2. I put that in right here for this. Okay, so what do I need? I still need the plus 2, and it needs to be cubed minus 1. Okay, so the minus 2 and the plus 2, well, that goes away. So I have the cubed root of 51 being cubed, not plus, minus the 1 out here. And the cubed root gives me the 51 minus 1, which gives me the 50. And sure enough, we got out the 50 that was the input a while ago. Now, the true test, we haven't proven, we've just verified for ourselves that this seems to be working and seems to be the inverse, and it checks our work. But it's not a proof. Okay, to prove that these are inverses of one another, I need to do a composition. So I'm going to compose f of this guy that I think is the inverse. That means I'm going to take this guy, only where I have the x, I'm going to have a new input, plus 1 minus 2. So here's the function written down, but wherever I have x, I put in this composition notation, if you'll remember from last semester, means put this in for the input. So I'm going to take all of this and drop it in there. So I have x plus 2 cubed minus 1. Okay, well, I have it in here. Well, the negative 1 and positive 1, they go away to 0. Right? Negative 1 plus 1 is 0. Okay. All right, so now I have the cubed root of a cube, so they go away just like those went away. Okay, so I have x plus 2 minus 2, and I get out x. That's the definition of inverse. That when I do the operation, which is composition in this context, when I do the operation, I get the identity element. And the identity element under composition is x. Why is that? Well, take any function, like let's make up a new one, x cubed plus 1. Maybe I shouldn't have made it a cube. X to the 4 plus 1, to be different. Okay, but if I compose g with x, that means I write down g, but I put x in wherever the input goes. So x goes right there. Well, did it change? No, it didn't change. So x is the identity element under composition. And inverses of one another, when you do the operation, give you the identity element. So since f, composed of our proposed inverse, gave us the identity element, they are for sure inverses. Math made simple. Simpson math.